From the 3Degrees discussion studio, I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
Anyone who makes something that has material property requirements needs to get those analyzed by not only a third-party entity, but a third-party entity who knows what they're doing. And that's where the accreditation stand in, right? We know what we're doing.
That was David Scannapieco. David is a scientific development management manager at NSL Analytical. David is an experienced researcher with an interest in mechanical characterization, reliability testing of materials, and the development of novel metallic materials through additive manufacturing. Before we get started, head over to www.3degreescompany.com and subscribe to the podcast. Remember, you can listen to the show anywhere you download your podcast, including Spotify, Apple, Amazon, or Stitcher. Also, if you or anyone in your company are looking for materials, qualification, or general AM support, reach out to the team through our website or via email at info@3degreescompany.com. Cool. David, well, thank you so much for joining the show today. Excited for the conversation here. We only recently met, so this is going to be our first talk, so it'll be good. Like I do with everyone, really like to start at the beginning. So where'd you grow up? What were some of those early years like? And did you have kind of an early inclination to engineering and materials back in the day?
Yeah. I've got quite a story. I grew up literally all over the world. Born in New York, went between there and Texas a couple times, moved overseas to Abu Dhabi in the Middle East for a couple of years, and then came back to Cleveland, Ohio, where I started college, and I've been here ever since. But in terms of, I always knew I wanted to be an engineer. What type of engineer changed throughout my life? You know, as a young kid playing video games, obviously computer engineer got pretty high up on my list for a while, but I knew actually that I wanted to become a materials engineer when I went to college, because I had started running triathlons. And as I was researching bikes, the bike frame itself is made of a lot of different things: steel, aluminum, carbon fiber. There's a couple other ones, but the big thing was researching them and wondering, okay, what's the difference, right? Like, why is steel so heavy when aluminum can also hold a person just fine on a bike? And also, like, why is carbon fiber so expensive? Like, you know, all of this is what's going through my mind as a high school kid. And then touring colleges, I found out that these are essentially questions that materials engineers ask every day. So I knew that's what I wanted to get into.
It's funny. When I was starting out, I was a baseball player, and so so I liked every year they'd come up with a new baseball bat, whether it's aluminum, carbon fiber, titanium, whatever it was. And my first job first internship was at Easton. They make bike frames as well as they're most known for baseball bats. And so I always thought, like, hey, like there's some person out there deciding these material choices and crazy applications like bikes and bats or snowboards, whatever it might be.
Right. Yeah. That's a funny coincidence. I actually really wanted to get into bike manufacturing when I first started college. I never had the opportunity to do that. But it was something that I was trying to get into. I ended up falling into the forging industry and worked
hopefully
at a
not
hammer.
Literally.
Yeah, thankfully not literally. But I did end up at a hammer forge. And I don't know if you've ever had the opportunity to sit and watch a hammer forge go, but I mean, these are car-sized blocks of steel that hammer down on red hot, titanium billets and things like that to form them into, and we were an aerospace and energy forge, so they're basically making engine parts. And I could sit there all day long and watch these huge hammers just wail on this metal, which it is kind of what led me to, like, okay, metallurgy seems like a cool field to do, And and then I found myself enjoying research as an undergraduate student. Um, Went after a internship at NASA. Got rejected a few times, but eventually made my way in there. And my first internship at NASA was to do powder characterization for additive manufacturing.
Which
Um,
which which group or which NASA spot?
I was at NASA Glenn Research Center here
Okay.
in Cleveland, Ohio. So I mean, they do. The group I was with was the high temperature and smart alloys branch. So I don't know if you've heard of like GRX 810, which is a pretty novel alloy that's just become public in the past year. Then you've got like shape memory alloys where they're making rover tires out of them nowadays. Um, they do some really awesome stuff, and so that's where I started with powder characterization, moved my way up into bulk material characterization, and then started my PhD with NASA Glenn Research Center on my own alloy development project. Um, so, and that's hopefully coming to an end this year.
And did you have a so throughout that time, like you kind of kept narrowing it down, right? It was materials and it was metallurgy. Like it seems like a big problem space to go and develop your own alloy. Like were some of the driving, like what were some of the constraints in that, or what was a specific use case, application, or kind of interest area that you were really targeting?
Yeah, I really what happened is that I'm just always very curious. I love learning new things, love to have new experiences and stuff like that. And so, like you said, I kept narrowing it down, kept thinking, all right, metallurgy, let's go try a bunch of stuff in metallurgy, do a bunch of weird things when I went back to school to research. Um, and then to narrow down into this, well, narrow down in quotes into this alloy development spectrum, which is actually really broad because what happened was my mentor at NASA, Dr. David Ellis, he had, for his PhD many years ago, invented this alloy GR 42. It's a copper chrome niobium alloy. And at the time, it was a candidate to replace combustion chambers in the shuttle program for the propulsion technology. But the shuttle program shut down in the early 2000s. And so the alloy kind of got sidelined until additive manufacturing started picking up. And they found out that while pure copper is pretty challenging to work with, the GR alloys, just a little bit of chrome and niobium that you add, makes it so easy to print in additive manufacturing. And so NASA has put a significant amount of resources into developing additively manufactured combustion chambers made from GR. And so, of course, you're right. The question that NASA asks is, all right, what's next? Right. This thing prints well. We can make a combustion chamber. That's done. What's next? And so the work that Dr. Ellis and I were doing was to say, okay, well, what if we could, you've got these layers of powder. What if we can change the composition, say it at every 10 layers or so? And even better than that, what if we remove the gas atomization step that's in GRCOP 42? Because it's a relatively expensive step. You would need to be very careful that there's no excess niobium in the material. And so my PhD was on in-situ alloying GRCOP 42, and with the desire to get to a point where we can gradient the properties of the alloy, because it's a very simple exchange of pure copper matrix, chrome 2 niobium, strengthening dispersoids, and the more dispersoids you have, the lower the thermal conductivity, but the higher the strength, and then vice versa if you have less. And so in a combustion chamber, the trade-off of strength and thermal conductivity is extremely important. And if you could focus where you're doing that, within the actual structure, you basically use materials as a new design constraint, or remove the constraint of design in your properties, you get more efficiency. You can get thinner walls that are better in terms of weight, especially for rockets, where it's $10,000 a pound to get something into low Earth orbit. You could save hundreds of thousands of dollars just by removing a few pounds of copper from the engine. So that's the work that we've done, and it went relatively well, especially considering the effect that COVID had on NASA and their ability to do work. But yeah, and I guess to circle back on the question of narrowing the scope, the funny part is that the alloy development work was extremely broad. I worked with elemental powders, did ball milling, did 3D printing, did wet chemistry experiments, did microscopy, microstructure experiments, then into mechanical testing as well, failure analysis. I mean, literally the whole gambit of materials that you can work with, except for raw ore, I did it during my PhD. And so it's got me this uniquely broad perspective for having such a niche degree and a niche topic in terms of analysis of materials.
So with the kind of in situ processing or gradient, is the mechanism within that laser power, or kind of if like how much energy you put into a given layer can impact the chemical composition of the final solidified alloy?
Yeah, it's not quite chemical composition, but the properties. So
Okay.
GRCOP is a unique case where the chrome and niobium have an extremely high energy to react. It's a very fast reaction, and it occurs almost instantly as long as it's within the liquid copper. Once copper is solid, they can't quite find each other. And so the longer you keep copper liquid for while you're 3D printing, the larger your precipitates or your dispersoids can get. And so then you have a weakening of the strength with larger dispersoids. So trying to find that perfect spot where you're getting everything liquid enough to spread and fuse and melt the chrome and niobium, but then moving the laser off of a spot fast enough that copper solidifies and the chrome and niobium don't have a chance to grow obscenely large. That was the fine tuning that we had to do. The process was pretty readily capable of happening. We didn't have much difficulty on the reaction side of things.
And how do you go about that? I mean, we talked to a lot of folks doing 3D printing design of experiments. So like talk us through kind of what was your process in that, and thinking about how to measure it, how to kind of keep in mind that this is sometimes can be a long process of like getting a build going. There's other people working on the machine potentially. Like what was your, what were some of those fine tuning things that you approached this problem with?
Yeah, so we actually spent a little while doing and this was years ago, doing the whole shooting in the dark, print a bunch of blocks with different lasers, speeds, and powers, and see what comes out. And then we did get a little smarter about it, and we moved off of the machine entirely and took our powder over to differential scanning calorimetry, as well as elevated temperature XRD. And between those two experiments, we were able to effectively predict the speed at which the reaction occurs and the temperatures at which the reaction occurs, which is why I can so confidently tell you that as soon as the copper is liquid, the chrome and niobium just throw themselves together, because that's what we were able to find out. And so at that point, it's like, okay, we know how much energy needs to go into this weld pool to get the reaction to occur and to fully melt copper. And then it's a little back of the envelope calculations because the energy of the laser is not quite a perfectly reliable calculation.
And how do you map that back to like DSC and XRD, where they're just different timescales, right? Like you're blasting
Yeah,
energy into a
right.
powder very quickly with a laser versus like these things. Unless I don't know all the latest DSC, you may be able to get that
No,
fast, but like
you're 100% right. The time scales. So XRD was the slowest to heat up. DSC was the middle range, and obviously, additive manufacturing has an extremely high thermal gradient. And so we mostly leaned on the energy component rather than necessarily the temperature component, because as long as you can expect that you're putting in the right amount of energy to get from room temperature up to you've melted and then resolidified the copper,
Mhm.
you should be getting pretty close, right?
Right.
And so we still did parameter development in that space, even having that energy background, but at least we were targeted with it. And so there was a bit more it was a bit more elegant than just shooting in the dark. And it provides insight, right? If I wanted to go try to in situ alloy something else, a new material, um, the whole idea is that we don't have to do the whole broad guess in the dark kind of parameter development. We have a more pointed strategy to guide that process. And we've developed this strategy so that future work to try to repeat this with other alloys can be more successful or easier across the board.
I guess two questions on top of that. So you got a range, you can fine tune the the laser parameters, the machine parameters to get this in situ alloying. What are your methods for measurement? And that'll probably lead us into some good NSL fodder. But
Yeah,
if
for sure.
you're making a part,
Mhm.
how do you know you did well in that? And
Yeah,
then on top of that, like how you mentioned kind of the word gradient. Like I'm assuming you have like it's a gradient. It's a blurry line versus a sharp
right,
interface. Um,
right.
how much control do you have in terms of spacing? Is it just by like it's going to be bleed a couple layers? So if you have 40 microns, it's going to be like it's like 120 microns is kind of your
Right.
your edge. So what are your thoughts there?
Yeah, so you're getting to the edge of the work actually, which is great because this is the part that
And
I'm
we're
really
only 10
excited
minutes in.
about. And we're only 10 minutes in. Plenty of time for NSL stuff, right? Yeah, so we knew what our metric was going to be, and that was primarily going to be the phase analysis. So it's a two-phase material. There's copper and there's chrome to niobium, and maybe some excess chrome, but that's really it. Like two, three phases. Um, and so early on in the work, we wanted to confirm this with the traditional raw material so that we had a metric to compare to as we were working. And we found that the best strategy was to do a phase extraction, dissolve all the copper out because it's in the sense of this reaction, it's boring. It's copper when it starts and it's copper when it finishes, and that's
Yeah.
it. So we dissolve all the copper out, and all you're left with is the dispersoids um, that we can then do XRD on and understand all the phases that are existing in our dispersoids. And like I said, really there should be two. There should be chrome 2 niobium and maybe some elemental chromium. Um, and that was not the case in most of the work. We got a lot of oxides. We learned that even the relatively low partial pressure of oxygen in an AM system is not sufficient when you have liquid niobium. And and then also just COVID, everything shutting down for a year or two, our powder expired, and there's no money in an academic budget to go buy another $50,000 of powder to repeat experiments. So I say that we knew what our metric was, and we never quite perfected it, right? But all things considered, assuming you can reduce the partial pressure of oxygen in your AM system and not have expired powder to work with, you should be able to get that work done with a couple of tweaks of some engineering controls. It kind of leaves the realm of research and goes into the realm of development and fine tuning. And so we never really did start playing with what you can do gradient wise. But we know that the remelting was about 2 or 3 layers, depending on your parameters. And so you would expect some blurriness for, again, depending on your layer size, 100 microns or 200 microns as you're transitioning between layers. And I mean, that 200 microns is not a huge thickness for a blurry line. And honestly, the blurriness is far better than a sharp change. So I would almost let that, thinking forward here, if I was designing it, I would let that be a larger blurry line than our minimum capability. This is the kind of work that you get into when you're trying to weld two things together, and the weakest point is not either of the materials, but actually at the edge of the weld where you have like heat affected zone, because there's such a sharp contrast between the two materials as well as the temperature gradients that you get the weakest material at that point. So the advantage with AM and this potential gradient process is that you don't have seams, and you can blur it as much as you want and not have a single seam. And then your material, your weakest point, is going to be where your weakest properties are for whatever you're working with. So you could probably almost design in a failure point into a single component and know that it's going to fail exactly in one spot without having to do geometric effects just from material properties alone.
And so you kind of wrap up or in the process of wrapping up the PhD, did you ever have the thought of going into academia, like continuing academia, going to teach, or what was the transition out of academic life?
Yeah, I honestly, when Ed called me, I didn't quite know what I wanted to do. And what I get to do here at NSL is support all of the testing that I did for my PhD. I mean, we do ICP elemental analysis, we do XRD, we do microstructure, we do mechanical properties. So it's all the testing that I used to do for my PhD, I now support from a scientific standpoint. And I do have an interest in teaching. I have some plans to start getting back into teaching through professional societies and things like that. That's a next year thing, though. I'm still writing a dissertation. But academia, to me, it was not really ever on the table. Seeing young professors start labs right out of their PhDs, it looked like a very difficult process, and it just wasn't something that excited me so much that I thought I wanted to do it. I could definitely see, 10, 20 years down the line, leaving industry and going back to academia or something like that, and then starting a lab with something behind me. But it looks particularly difficult from a young professor standpoint.
And so maybe talk a little bit about NSL in terms of what you guys do and what you specifically do. I mean, you have material testing isn't unique to 3D printing. And I know with at their additive manufacturing. And for those who are listening, Ed Herderick is the Ed we're talking about, podcast guest somewhere in the 80s or 90s, I think. And I don't know I don't think he was at NSL at the time. I'd have to go back in terms of and listen to when he was there, but maybe just a broad description of what NSL is, and then we can kind of dive into some of the specifics there.
Sounds great. Yeah. So NSL Analytical, we're a third-party testing lab accredited through ANAB, NADCAP, and ISO. So those will make sense to anyone who's in the manufacturing industry. They might not make sense to other people, but what those are, they're certifying bodies where anyone who makes something that has material property requirements needs to get those analyzed by not only a third-party entity, but a third-party entity who knows what they're doing. And that's where the accreditation stand in, right? We know what we're doing. And so our processes are rigorously audited, and we have expert technicians and expert scientists and chemists who test materials in all stages of their life: raw material, final products, preformed products, everything. And we provide those results and make sure that what's being produced is being produced right and in the right way. And we provide that kind of support, failure analysis support, consulting support to all of our customers. And Ed Herderick and my charge, as both of us have been hired in the last year, is to bring some research and development to the table. So with my background in alloy development and in kind of advanced testing techniques, we're going to start bringing that into a more accredited and controlled light. And it's going to be a bit of a walk, but I think that we're capable of doing it here.
And is that specific to 3D printing? I mean, there's a lot of testing going on in 3D printing, but that's not necessarily all of the materials world.
Right. And 3D printing is a significant component to what we're here to develop for, because, I'm sure you have probably had guests on here who talk about the qualification of 3D printed components. It's not a trivial question to say, how do we know that our 3D printing processes are reliable, and how can we prove that they're reliable? Because, who knows? You buy powder from a slightly different supplier, and maybe the chemistry is ever so slightly different, and then your parameters are not quite as effective as you expect them to be, and it cascades. And so having that reliability is critical to the production of parts that are going to go into consumers' hands, be it spaceships, cars, or phones. We need to know that our materials are reliable, and what we're producing is reliable. And that's a huge part of the AM industry at this moment. I don't think I need to tell you that.
And what's the balance between, there's the mechanical, chemical analysis, right? That if you get a machine in the first 6 months, people are doing dog bones and Sharpie and density cubes and sending you powder samples. But at some point, people have to get to parts and geometries. How much of the testing of actual parts do you do versus coupons and more materials centric?
Yeah, so
coupons type of thing.
Yeah, from a non-AM perspective, it's almost entirely full parts. We've got a shop in the back that receives full forgings that they cut up and machine into utensils and things like that. And that's where we would want to get for the AM industry. There's just not as much production of true parts yet that comes through our window, at least. And so that's part of the advancement in the testing is you want to take advantage of thin wall additive manufacturing techniques, stacking parts in various ways. And so you just need to figure out the industry needs to find a standard for how do we approach thin walls, right? I can't pull a dog bone out of a thin wall sample unless we've adjusted what we define the dog bones to be. But that's ASTM has to write a standard. ANAB and NADCAP have to agree that the standard is good enough. Testing labs have to become accredited to do that new standard. It's I hate to say it, it's a multi-year process after the standard has been written in the first place, and we don't even have the standards written yet. So it's got a couple of years to go, guaranteed. But the effort is there and the ideas are there. We just need to keep moving on it, really.
And what do you see as kind of the maturity of most customers that you're getting parts from? Are these folks that are like, hey, we've invested in a couple of additive machines, we're starting to kind of tiptoe into production, but we need some help in a third-party lab to help validate it? Or is it like, hey, we don't have all of this machinery in-house, right? We don't have a tensile, we don't have a chemical, we can't test chemical composition. Like what's the balance? Are people like just are really leveraging you for the certifications that you guys have and the ability to do the tests, or just the machine capabilities and say, okay, hey, we need a partner just to do the materials testing for us?
Right. It's pretty evenly spread, to be totally honest. There are a lot of additive startups that have their ideas, they're interested, they're eager, and they're trying to make their own mark in the industry. And along with being a startup, they don't have the money or really the justification to go buy a tensile machine, an ICP machine, a couple of LECOs to do oxygen identification, right? And so we love partnering with them to help them develop their material. And then we also have several customers who are more or less producing real parts, and they might have some of their own capabilities in house, but maybe they have other priorities, right? And so we're a backup lab in some cases, and in other cases, they have an ICP machine in house, so they don't have a tensile tester, or vice versa. And so we do the alternative. But pretty much, I mean, one of our major selling point is our accreditations. That they're no small feat, and certainly, no matter where your stage of development is, if you say, hey, look at these properties, these are accredited testing properties, I mean, that is a feat, to have developed a product that can consistently develop properties from a third-party lab, whether it's us or whether it's somebody else. It's a feat. That's a great accomplishment for anyone.
How much of the engagement do you do with designing testing experiments, right? It's like people send you tensile dog bones, like you can get them just kind of say whatever, right? I mean, right. The number is the number, but like how they use it, you probably don't really care, other than like, hey, this is your data sheet. Like, right. How much of it is upfront? Like, hey, maybe you should structure it in the sense that don't put all the dog bones in the middle. Maybe do some different axes. Maybe do some taller parts or whatever it may be. But are you getting into that level of, I guess it's more consulting versus testing?
Yeah, that's actually it surprised me when I started here. It's a very standard thing to do when talking to customers. We talk to a lot of customers who are experts in their application and are experts in their design, but are not necessarily experts in materials characterization. And so they might know that they need to check out certain aspects of their material, but there's a lot of techniques that could get you there. Do you want to do optical emission spectroscopy or spectrometry, or do you want to do mass spectrometry, or do you need to leave ICP entirely and go to something else, right? Just from an analytical chemistry perspective. And so I would say I'm on more than one call a week where we're talking to customers, five or six maybe total a week, where we're talking to customers, understanding what they're actually looking for, and then providing some insight on how to get there in, a cost effective, a time effective way. Um, and then the material constraints again are also not an insignificant challenge, right? There are some elements that don't play nicely in certain analysis techniques. And so we have to steer them towards other things because they're just not going to get a high quality answer. Um, and I wish I could. The only example I can think of is a little bit out of the fantasy realm, but like when you're doing oxygen, carbon, sulfur analysis, working with something that has high refractory alloy content is challenging because they're so high temperature that they kind of gum up the machine, and you just don't get the high quality readings that you get on something like nickel or something like that, nickel based alloys. And so it's having that expertise of the actual tests uh, that we also provide to customers on a very regular basis. It's a very normal thing for us to talk about. So it's not, um, yeah, not a, and anyone who's worried about not knowing exactly what tests they need to do should not be afraid. We'll happily help you out.
What are the, I guess, what are the top three tests that you see for additive parts? If I had to guess, it'd be fatigue, tensile, chemical composition in that order.
I might throw chemical above tensile,
Okay.
but fatigue, but those are the three that I would go after immediately
Yeah.
too. Fatigue is so critical, especially for AM. Part of the work that the team that I was a part of at Case Western Reserve during my Ph.D. did an extensive fatigue analysis of Ti-64 additively manufactured and found that even when you think you have ideal parameters from a metallographic standpoint, right? You've done your porosity imaging and you've found there's nearly no porosity. You're at 99.9 plus percent density. You can still get these tiny little defects that a fatigue crack will find and will initiate off of and will fail early because of it. Um, and again, it leans into the qualification. How do we know that we got reliable material coming out every single print? Um, you just can't have a 2 orders of magnitude span on your fatigue lifetime. It's untenable to work on a design space that has that kind of uncertainty. Um, and so part of this effort was to help illustrate that and maybe illustrate ways that could be mitigated. I was only partially involved in it, so I don't quite have all the knowledge of everything that they've done. I did a significant amount of fractography for them, but uh, it's a challenge to make sure that the fatigue properties are where they need to be, for sure.
And so last couple of questions as we wrap up. I mean, what are you excited for looking out kind of the next 6 months as you kind of get your career started at NSL?
Yeah, I am excited primarily to start doing more educational things. I love nerding out about material science, love nerding out about material characterization. Ed and I have recently started doing little posts on the NSL Analytical LinkedIn about different testing techniques and details, and just getting real nerdy with it. So that's really exciting. I'm also excited to continue to learn. I've been in and this sounds like complaining, and I'm not complaining. I've been in such a well of high temperature alloys for space applications You start to think that that's the only thing anyone ever cares about. But there's a lot of other cool stuff going on in the world. One of my large charges is to learn about batteries, for example. I'm a metallurgist by trade, and I need to go learn about batteries. And there's a lot of stuff going on with batteries that are very, very cool. So I'm excited to be in the position I am because of the breadth that I get to go after and learn about.
Awesome. And last question I asked this of uh, everyone is like, what's a book recommendation? What's a favorite book, favorite thing that you gained a lot from either in your career, personal life that you'd like to share with the audience?
Ooh, uh, I will. So actually a big nonfiction reader, and so there's a book. Actually, I think I have it right. It's called Rain by David Epstein. It kind of talks about the power of having broad knowledge, and how that can help you overcome challenges. And sometimes, some cases, better than being a niche, bored in a hole kind of a person, um, or an expert like that. So go out and learn some weird stuff and see. That's my recommendation.
Fantastic. Well, David, thanks so much for joining the show. I look forward to seeing you in the conference circuit, I'm sure, one of these days.
Yeah. Thank you so much for having me, and it's great to meet you.